Oh, okay, okay. This talk is for quiz traverse. This talk is Petabyte-Scale. It's terrible problem. Let's welcome.
Thank you all for being here. So, at any rate, so my talk here is about building petabyte-scale Postgres clusters using something I'm calling Bagger. We'll talk a little bit about what this is, what it's designed to do, and the trade-offs that come with any large petabyte-scale deployment. If any of you have ever worked with Elasticsearch at the petabyte scale, you probably know that things that look like they work at 10 or 100 petabytes often don't work at 10 or 100 terabytes often don't work at a petabyte. So, yeah. So I've been around Postgres since 1999, so I have 25 years of experience with it. I've worked doing all kinds of things from application developer to database engineer. I've even contributed one patch for a race condition that was happening with Postgres. So I have a lot of experience with this. I love to go to conferences and talk, and I usually talk about either big Postgres deployments or the need for us to have human factors training in IT operations, particularly databases. So that's me. Always happy to talk more about these topics, but we'll probably want to go right into the agenda since this is a relatively short talk. So I want to cover basically 5 things here. First, why at a place where I used to work, we built a project called Bagger. The general design of that early version, some shortcomings, and then a design of an open source replacement, which I'll provide the GitHub link and some other things there for anybody interested. And then trade-off lessons, because I've worked with multiple petabyte scale deployments of basically fleets of Postgres servers. And depending upon what you're trying to do, your design decisions may end up being quite different. Right? So Bagger is designed around one workload. If you need to do something like a distributed data warehouse, you're going to have to think about problems differently. So life before Bagger, when I was at Adjust, we used Elasticsearch, and we had 1 petabyte for 30 days of data. We were only retaining 30 days. We had 1 petabyte, and velocity made that system 100% unusable. In fact, the overall joke was it was an extremely expensive dev null. We could write to it. Oftentimes we couldn't query it. And if things went down, they would go down catastrophically. Specifically, we had several specific problems with Elasticsearch. Some of these have gotten better as JVM technologies have improved. Others of which are sort of inherent in Elasticsearch's design. These make it very convenient to use at 2 or 3 terabytes. They make it extremely difficult to use at 1 petabyte. And last time I talked to Elasticsearch teams, they didn't have anybody using it above 1.5 petabytes. So the first one is that to store a very large amount of data in Elasticsearch, you have to have a large number of instances. And those instances all talk to each other. In a lot of cases, anytime like a new field is discovered or you have a lot of state information that exchanges hands. And this leads to poor performance in a lot of areas. You'll have ingestion waiting on quorum, for example. You will have, when you have a new field discovered, you will have the question of what happens when one node goes down and you have to rebalance. And consequently, at a petabyte or larger, Elasticsearch is extremely difficult to start or restart. And this is because, adding a node to the cluster or removing a node from the cluster forces a whole bunch of things to happen that eat up a lot of network traffic. Another major problem that we had, and this has probably been resolved since, is that garbage collection stop the world events would knock nodes out of the cluster. This was because we would run with about, I think, hundreds of gigabytes of RAM basically allocated to the Java stack or the Java heap, and when you would go through to sweep, mark and sweep, this would sometimes take minutes. So the software pauses for minutes, it misses its heartbeats, it drops out of the cluster, everything rebalances, that eats up more, that puts more stress on everybody else's garbage collector, and sometimes you can end up in a cycle, sort of a graveyard spiral, if you will. The other major graveyard spiral we would hit was what happens if somebody would run a query that would exceed the heap limitations of one of the nodes. And this is, what would happen is you'd get a Java heap exception, and then the front-end libraries would very helpfully retry the query. So you've just knocked a node out of the cluster because it had a Java heap exception, it's resyncing, and now you just repeated that query and you're gonna knock the next node out. And then you're gonna repeat the query and you're gonna knock the next node out. And then you're gonna repeat the query and then you're gonna knock the next node out, and so forth. You can imagine the kinds of problems that we would have working on that kind of scale. One of the things we also had to do is we had to use very fixed schemas. And the reason is Elasticsearch has all the schema discovery logic. It's all very heuristic. You see a new field, it will pause ingestion while it tries to figure out what to do with that field. It will assign an index to it, and it's very heuristic about the types of that index. It may get them wrong, and then you may have more problems down the road. So we had to have extremely specified upfront schemas, which kind of defeats the purpose of trying to use Elasticsearch in a NoSQL type way. Some of these have gotten better. The garbage collection ones in particular, I think, are much, much improved. However, it's doubtful that all of these have improved to the point where you can use it at, say, 2 or 5 or 10 petabytes. And so we had to move from Elasticsearch. We needed something fast. We evaluated a bunch of technologies, and then we built our own. The idea was minimalist design, fully schemaless. We specify indexes. We don't specify document schemas. That it would be linearly write scalable forever. And it was built for write-heavy, read-seldom workloads. So this was built specifically for log management, where you're going to write very heavily all the time, but your read scalability doesn't need to be there. And so, in fact, read scalability was more or less static, well, probably closer to logarithmic, but logarithmic scalability isn't very good, right? So the Just design went through things like this. Basically, the log messages would get written to Kafka, and the partitioning systems of Kafka would effectively map to shards of the log management system. So everything's randomly sharded. We had a custom we called data shuffle called Shuffle, which is German for shovel. And it was basically what would load from Kafka right to Postgres. We did have to patch Postgres, trivial patch, just to bump up the number of columns we could have in indexes, because we didn't want to index every field of the JSON. So we just bumped up max index keys so we could have a multi-column index with like 55 columns, which you can't do in generic Postgres. And then it just stores JSON-B documents. We filtered out things with embedded nulls and other things that Postgres can't support. And we used a C language routing trigger. So very minimalist design. Everything comes in. It has much of the same. It pulls some ideas from Elasticsearch, but basically strips down a lot of the coordination to the minimum, bare minimum. We wanted to open source it, but we couldn't just like release the source code because there were a lot of assumptions to adjust internal business and operations, and you don't open source software when that's the case. There was a lot of statically defined partitioning criteria. That was one aspect of that. And a big part of the problem here is that we wanted to fix all these, but we never had the time or budget. So Then I left Adjust, fast forward about 2 years. I ended up getting together with a bunch of other people who had left Adjust, and we thought, hey, you know, this was cool technology, but maybe if we rewrite it from scratch, we can get rid of these problems and then we can open source it. So we designed a similar system. We are using open source components. Everything will be open source, and I'll show you I'll give you the GitHub link if you want. In fact, it's permissively licensed for reasons we can talk about later. The design strategy for version 1 was very simple. Go with what we know. Minimize unknown unknowns, because when you're working at the scale, if you change something, you really don't know the full footprint of that change, right? And so we decided to build something as close to what we had previously worked with as possible, while at the same time making it generally useful for everybody. And then the idea was we could evaluate larger changes independently later once we have a baseline that is similar to what we had built before. So remember, we already had an experience with this prototype, and when I left Adjust, it was at 10 petabytes of data, and we were only retaining 14 days of data. So we were able to ingest hundreds of terabytes per day. So this is why go with what we know, and then figure out what else we want to solve later. So going with what we know. A lot of things here are going to go, why would you build software in 2024 with these technologies? Again, because we understood where our limitations were. And if we start pulling these things out for version 1, now we're in new territory, and we don't know where we're going to be. So the first version was written in Perl for certain pieces, so we wrote this version in Perl. But since we're going to go with a more modernized Perl, we used Moose, which anybody who works with Perl 5 would know is a really good object-oriented system for Perl. In fact, I think it's one of the best object-oriented systems out there anywhere. But you know, a lot of people don't like Perl today, so can't use Moose. And then a framework that I had written like almost a decade ago called PGObject, which makes it real easy to direct logic from a Perl application to user-defined functions in Postgres. So we could build a lot of the functionality in the database and then just have a really light Perl layer that did as little as possible. That makes it easier to switch out Perl for something else later when we're ready to, right? The C language triggers are going to stay, I think, because we need something hyper-performant, and like it or not, there is no alternative to C in that regard, right? Even Rust doesn't perform as well as C, and while there can be reasons to put Rust inside the Postgres system, this is not a good application for that. If you're going to have a web interface for Perl, you might as well put it through Perl Dancer. We haven't really decided a front-end framework because the Adjust system didn't have a real front-end. And then we have decided to add etcd for cluster state handling, although this is now pluggable, so it's trivial to write a plugin to do that state management via Zookeeper console, or technology of your choice. You could even throw it through another Postgres instance if you really want it. But we're providing basically the pieces for running through etcd. So that's the initial technology choices. So at this point, I want to discuss how our design is different and basically what our current design is, and then talk about some of the trade-offs. So here's our data flow. This is how the data gets into the system and how it's managed. So you have a service network. This is a network where log messages are being generated. They get written to Kafka as JSON documents. Then we have a bunch of Shuffle instances. They read from Kafka. This will read from a set of partitions, and they will write to 2 different Postgres systems in kind of a wheel rotation, right? Then the nodes themselves are running databases, Postgres databases, and the C language trigger will direct it to a partition based upon your configuration. And then that's basically how the data gets stored. On the other side, we start off with the front end, and the front end will call a REST API. This part here, which will hit a piece of software we call a query proxy. The first version of that will be written with Perl Dancer. We are strongly evaluating 2 other languages to replace it on the second version. One is Golang and the other one is Java. We have not decided between those 2. And then the query proxy makes queries to every other node and then coalesces the results and basically streams them to the front end. Because we could be dealing with very large amounts of data, we actually try not to store anything in memory in the query proxy in this regard. We just try to ship it to the front end as fast as we can. So for the superstructure, this is the control structure. We call this the shuffle rod, the shuffle circle, the shovel wheel. We have the metadata servers, which basically do a lot of control operations. And this basically fans out through etcd to basically deliver desired state information to all of the bagger nodes. And then those bagger nodes the data nodes will effectively reconcile their state to whatever's in the etcd. Then the query proxy will query the metadata servers to determine how to query the data nodes, and all of it will be orchestrated through infrastructure as code. So the current status is the node control infrastructure is pretty complete. Not fully tested, but is pretty complete. The metadata server schema and functions are complete and tested. The C language trigger is in progress. I made some progress on that yesterday, and I kind of expect the C language trigger to be finished up in the next couple weeks. We have a PostgreSQL config done that will help export metadata via a REST API. The query proxy, sorry about the typo there, is not done, and the front end is not done. So we'd love to have people get involved, but obviously this is a niche area, so if you don't want to, no hard feelings. Beyond the first version, here are some things we really want to evaluate. Better language for the query proxy. I mentioned Java and Golang. We have also evaluated C. C has some advantages, but writing a web service in C doesn't really seem like a very pleasant thing to do. So probably Java and Golang are most likely to be the finalists there. Another question is, do we want to integrate CitusDB? Does that provide benefits or drawbacks? If so, how do we integrate it? We'll have to evaluate that. My naive assessment is that probably CitusDB would limit write scaling. Just because you're routing between nodes on the right side, there might be some ways around that though. How can we scale reads? Right now, read scalability sucks, right? We've traded read scalability for write scalability, which is usually not what you do. Normally you go the other way around, right? We can probably scale reads by adding read replicas, but now your costs go up linearly with writes and linearly with reads. So if you have to double your read and write output, you have quadrupled your cost, right? So maybe that's not the best approach, but we'll have to evaluate that. And then there are some things inside of Postgres that we're going to have to evaluate. If we change the block size of Postgres, how does that affect things? If we compile Postgres with 32K blocks, can we remove most toasting for many users? What impact will this have on performance? Just as a show of hands, who here knows the term toast in Postgres? Only a few. Okay. So Postgres, if you stores everything in 8K blocks, but a single column value can go up to 1 gigabyte, right? So the question is, how do you store more than 8K in a block? Well, you don't, right? What we do instead is we move it to an external storage, and we typically compress it and chunk it, right? That's toasting. So if many of your JSON documents are say 10K, if we go up to 32K and we say, please avoid toasting this value, maybe we can get better performance, or maybe we can't, and we've got to benchmark that. Because maybe then that would mean that it all goes into, inline storage, and when you query, you don't have to piece together and decompress chunks. So those are sort of on the top of our list. There are a few major trade-off lessons. I'll be done with this in a couple of minutes, and I can take questions at that point. The first one is that whatever you do, you're going to have trade-offs at the scale. And one of the ones we focused on here is read versus write. So in this case, this is for write-heavy, read-seldom workloads. So we can trade off linear write scalability for very little read scalability, right? On the other hand, if you need to scale reads and writes, now you're going to have a more complicated architecture. You're going to have to do tuple routing, right, on write, and so you're going to have multi-layers where you can scale all those layers independently. Another lesson is benchmark everything. When we had written the first version at Adjust, we had settled on the technology only after extensive benchmarking. We had decided not to use ScyllaDB, for example, because the I/O performance was not as great as it was on Postgres. So because we wanted to optimize that, we went with Postgres. And the second one is specialization versus generalization. This is, always going to have, once you're in this corner of the market, you're probably going to have to specialize, and many of the generalized solutions may work for some set of problems, but they may not work for your set of problems, right? So to get the performance you need, you may have to write something that's much more specialized than something like Citus, for example, where Citus is a very good general tool. A couple of bonus learnings. Know your requirements. If you're working on the scale, changing requirements can have architectural implications, right? And architectural implications are expensive. So making sure that the requirements are well understood before you start in this sort of case is actually really important. In a lot of other cases, don't have to know the requirements so much that you can iterate. In this sort of case, it's a lot harder. Different architectures are going to serve different needs, and this is one of the big aspects there, right? When I was at Adjust, we also had a distributed data warehouse that was also in the petabyte range, and that was a whole different fleet of servers, right? And structured extremely differently. Linear scaling in one dimension is much easier than linear scaling in multiple dimensions, right? If you want to scale writes or you want to scale reads, independently, they're relatively easy. If you need to scale both at the same time, it's much, much harder. And so those are the major bonus learnings. So I'd like to see, we have a few minutes for questions. I'd like to try to answer any questions that anybody might have. Any questions? Okay. It's coming in with the microphone.
How many nodes did you use when you had the Elastic machines?
So I think we had like almost 40.
And were they physical nodes? Because you mentioned they had
these
a
were
lot
all
of
bare
RAM.
metal. These were bare metal nodes, yes.
Yeah. And then
and when we went to Bagger, we cut it down to like 20.
yeah, makes sense. Have you looked at ClickHouse? Because it seems
Yes.
like a lot of
ClickHouse is very interesting in this regard. I think it's a very interesting technology. The sorts of guarantees you get in terms of atomicity are different, so you have to build your application around those guarantees. And there are a number of workloads which push ClickHouse into really weird pathological pieces. So it's fine when you're bulk loading data from Kafka and you're basically just using the Kafka adapter. However, if you're setting up, say, one insert every second, ClickHouse will die. right? So ClickHouse is a totally different beast, and it has totally different positives and negatives attached. I would actually like to add features in this area that would compete more with ClickHouse. It would, for example, be able to take stuff from the stream, create Parquet files that then we could do like LSM merging across. But that's somewhere down the road. It's not going to be in the first version for sure.
What was the C language trigger?
The C language trigger basically takes an inbound JSON document, and it looks at pieces of the JSON document to determine which table partition it needs to be written to. So that means that we can then prune periodically and deal with retention issues and stuff like that seamlessly, and that the shuffle system doesn't have to know the internals of the partitioning.
So do you do rebalancing?
So we are not including rebalancing in the first version because rebalancing is protocol heavy. And this is one of the things that can get you into trouble. What I'd like to do in future versions is to add a separate rebalancing job that can basically go through and rebalance when the administrator says it's necessary. This would avoid a lot of the automatic state handling that can cause problems at scale in this regard. So,
was there another question? Because then the last one would be like, why did you choose Kafka as part of the design?
So we had chosen Kafka just because we had a lot of Kafka and a lot of knowledge of Kafka in that place. In theory, because of the way Shuffle works, we could write adapters to other bulk queue delivery systems like Pulsar or Red Panda. I don't think we'd want to do it for like RabbitMQ because we need to be able to do the bulk loads, but it could, these things already exist for, say, reading bulk from Redis queues that would be Redis lists and writing them elsewhere. So it doesn't have to be Kafka, but Kafka is what we're currently using for doing the partitioning because it's what we had. We could write something else if somebody needed it. Every data is written twice, so if a node goes down, you still have a copy of it. And the idea is that
First in the Kafka and then into the Postgres, right?
yeah, data is your question is about ingestion. Yes, data is written first to Kafka and then to Postgres.
And then if something happens on the Kafka side, we lose the data.
If you lose the data in Kafka, then it will never get written into Postgres. Your question is about if data is lost in the Kafka side, then you can lose that data that's currently buffered, and that's correct. You need to have, ideally, a fault-tolerant Kafka setup. So I strongly recommend in these cases having fault tolerance on the Kafka side as well as the Postgres side.
Okay, thank you all.